right, welcome back to operating systems. So today will be a nice reprieve from your brain breaking from having multiple processes running, different address spaces, file descriptors, all that stuff. So for today, has anyone ever stood in a line before?
Line of what?
A line
Line of what?
at getting food.
Oh,
Yeah, all right. So if you've ever stood in a line before, this lecture will be fairly straightforward. So we're just going to be talking about lines today pretty much all day. So basic scheduling. First, we can do some boring stuff. So there's two types of resources on your machine: preemptible resources and non-preemptible resources. What does that mean? A preemptible resource is something that can be taken away at any given time and shared. So a CPU is an example of a preemptible resource. I can stop a process from executing, let another process execute for a little bit, go back and forth. Maybe if you have siblings, you had a preemptible resource, some toy or something, you could share that toy, whatever. So it's shared through scheduling. So you can schedule time with that resource, and then each of you can take turns or do whatever. A non-preemptible resource is something that can not be taken away without some type of acknowledgement. So for example, disk space. If I'm using a gigabyte for a file, I can't just say, hey, you can go ahead and take 100 megabytes of it and just give it back to me when you're done, because that wouldn't make any sense. They'd use it, you'd lose your information, you wouldn't get it back, it would just not really make sense. Another example of this, something like memory, actual physical memory. So you allocate and you deallocate memory. So you use it, and then when you're done with it, you return it. So for like super high performance computing, if you ever get into that, sometimes you might find out that CPUs are a non-preemptible resource. So you can actually allocate a CPU to your process, and then you are guaranteed to be the only one with it, and you will have some nice performance characteristics with it because you know nothing else can ever take it away from you. But that's not in this course in general. CPUs are preemptible, you have to share. So there are two things. There is something called a dispatcher and a scheduler that works together. We've already kind of talked about the dispatcher. It's just the name for the low-level thing that actually does the context switching. So whatever is saving state and loading state, that is doing the context switching to switch between executing two different processes. That's what the dispatcher is doing. So the scheduler is the high-level policy that we will talk about today, and that is responsible for deciding what processes to run and sometimes when. So we can start this super simple. The scheduler will run whenever a process changes state, so we can first consider non-preemptible processes. So a process just runs until it is done. So this is like uniprogramming systems. It just runs until it's done. The scheduler only makes decisions whenever a process terminates, exits, and then the scheduler has to pick another process to run. So preemptive, just so if you've ever run uname-v before or looked at it, that will tell you like the date your kernel was built and like options of it. One of the options it will show you is preempt. So now you know what preempt means. It means it's a preemptible kernel. It can interrupt processes at any given time. So when we talk about scheduling, there are four main metrics. So the first one is minimizing waiting time and response time. So you don't want to have a process waiting around too long. So like it wants to execute, you want to give it the CPU hopefully as quick as possible and let it finish and let it terminate as quick as possible as well. You also want to maximize CPU utilization. So you don't want to have a CPU idle. So that is especially important if you have multiple cores on your machine. You don't want a core idle because it's not really doing anything. The other one is throughput. So throughput is just running as many processes as possible and ending them. And the last one is fairness, which is kind of at odds with all the other ones. So you want to try to give each process the same percentage of the CPU and essentially treat them all fairly. So first algorithm, not really an algorithm. It's first come, first serve. So that is actually a form of scheduling. So it just means the first process that arrives gets the CPU. Processes are stored in a FIFO queue, first in, first out, if you don't remember what that means. So it's just like a normal queue if you go and get food. So it maintains this queue in arrival order. So whatever arrived first is at the front of the line. So throughout this, yep. Yeah, so for now, we'll just talk about a single CPU core. You just run single core at the time you get the whole CPU. So for this, we'll consider these processes. So let's consider 4 processes. I'm super creative with names, so I name them P1, P2, P3, and P4. And then this column is the time they arrive at. I'm not going to use time units. I'm just going to use like just atomic time units. So I won't use seconds or anything like that. I'll just do it in time blocks that I won't have fractions of, just to make our lives easier. So they all arrive at time 0, and then the burst time, that might sound like a weird term. Burst time just means how much time will this process actually execute on a CPU for until it's terminated. So process 1 wants to execute for 7 time units, process 2 for 4, process 3 for 1, process 4 for 4. So since they all arrive at time 0, I have to explicitly tell you their arrival order. So here, I'll assume that they arrive P1, P2, P3, P4. So if we have first come, first serve, this is our schedule. So we just run P1 because it was at the front of the line. It runs for 7 time units. Then whenever it's done terminating, whenever it's terminated, then we have to pick what process to run next. In this case, P2 is next. We'd run it for its 4 time units. Then after that, P3 is next for 1 time unit. Then P4 finishes it off for 4 time units, and then we're done. Any questions about that schedule? Fairly straightforward. Yep.
How is the burst time calculated? Like, what if the process takes longer than it's expected?
So in this case, this is like the true burst time. This is how long a process will take, which on a real operating system, you won't know that, right? So we're just setting up a framework for dealing with this. Generally, you analyze scheduling stuff after they've already completed, so you know how long they run for, and then you kind of do like a post-mortem and figure out, the average response time and all that stuff. So in this case, if we wanted to figure out the average waiting time, well, process 1 waited around for 0 seconds. Process 2 waited around for 7 seconds because it also arrived at time 0. Process 3 waited for 11. Process 4 waited for 12. So to calculate average waiting time, no tricks. 12 plus 11 plus 7 plus 0 divided by 4. So in this case, it's like 7.5, I think. So there could be a slightly different order. So if we assume that our order is P3, P2, P4, then P1, now this is our schedule. So we'd pick P3, runs for 1, then pick P2, which runs for 4, then P4, which runs for 4, and then P1, which runs for 7. So if we did the same thing and calculated our average waiting time again, it would be 0 plus 1 plus 5 plus 9. So if we calculated it out, it would be 3.75, or half of what it was before. So you might think, well, first come, first serve is pretty bad because the average waiting time varies wildly between just whatever order the processes happen to come in, which generally isn't, generally we want our systems to be fairly predictable. So first come, first serve, it's an algorithm, it's not the greatest. So if we wanted to minimize average waiting time, we could do something like shortest job first. So it's a slight tweak where we always schedule the job that has the shortest burst time first. Again, we still don't have preemptions. So the only tweak I'm going to do here is change the arrival time of the processes so that they don't all arrive at time 0. So P2 arrives at time 2, P3 arrives at time 4, and P4 arrives at time 5. Then we'll just use the same example throughout the rest of the lecture just to compare them. So for all that, I always like drawing the arrival time on the top. So here I just draw it on the Gantt chart directly just to make things a bit easier when you have to schedule things. So our algorithm at time 0, there's only P1, so it is the shortest job because it is the only job. So we would schedule P1 for 7 time units, and then while it is executing, P2, P3, and P4 would arrive. So at time 7, we get to decide which one to run between those 3 processes, and the one with the shortest job is P3. It's only 1 time unit, so we'd execute it for 1. Then at time 8, well, there's a tie between P2 and P4, so to break the tie, you can just pick whoever arrived first. Yep.
Sorry, but is it possible that we sleep P1 at the time when P2 arrives and probably execute P2 first because it's shorter than P1?
Yeah, so the question is, hey, at time P2 at time 2, it's shorter, so can I just preempt it and switch to it? That would be better, but right now we're doing non-preemptible, so we're not allowed to preempt it.
Sure.
So that will be our next tweak though, so hold on. So if we do this and then we calculate the average waiting time, it just changes a little bit because some processes do not actually arrive at time 0. So P1, its average waiting time is 0. It arrived at 0 and waited for no time units. P2, its waiting time, well, arrived at time 2, and it waited for 1, 2, 3, 4, 5, 6 time units until it started executing. P3, well, it waited for 1, 2, 3 time units before it started executing. And then P4 waited for 7 time units because it arrived at 5, didn't start executing to 12. 12 minus 5 is 7. So its average waiting time now is 4. So the next tweak, well, first off, this isn't super practical. It provably optimizes the average wait time if there's no preemption, but on a real system, you're not going to know the burst time of every single process. Even if you did, it might change from process to process. This is something you could think of, you just throw AI at, maybe it would be good at it, but the longer the schedule takes, the worse because it's also counted as overhead, so you want it to be as fast as possible. And also there is this issue of starvation. What does that mean? Well, that means that some processes might never execute. So you can imagine if some system constantly gets a bunch of really short processes and there's this long process, well, then all of the short processes will just hog the CPU, and that long process would never execute. So for some reason, a process that never executes, the term for that is it gets starved, or your algorithm suffers from starvation. So we can do the tweak where we add preemptions. So to add preemptions to shortest job first, the algorithm just changes to shortest remaining time first. So we also assume that our minimum execution time is 1 time unit, so I can only preempt on time unit boundaries, so I don't have to deal with fractions. And then similar to shortest job first, this optimizes the average waiting time. So here is our schedule if we have preemptions, which was like your idea here. So at time 0, P1 comes in, and we have no other choice but to schedule P1. So we would schedule it for 2 time units, and then P2 comes in at time 2. So at time 2, P1 has 5 time units remaining, and the newly arriving P2 has 4 time units remaining because it hasn't executed at all. So 4 is shorter than 5, so we would schedule P2. So P2 would run for 2 time units, then at time 4, P3 comes in. So P2 has 2 time units remaining. P3 only executes for a total of 1, so it has 1 remaining. That's shorter. We'd schedule P3. So schedule P3 for 1, and then it's done. Then P4 would come in, so we have to choose between P4, P2, and P1. So P4 has 4 time units remaining, P2 has 2, P1 has 5. So we would schedule P2. It runs for 4 time units. Then we'd schedule P4, then P1. So if we calculate the average waiting time for this, so we can use a little bit of a shortcut. So if you want to do a shortcut and not count all the blocks in between here, well, for process 1, you can just figure out when it ended. So it ended at time 16, and it started at time 0. So that was the total time it was available to the CPU. So that total time was 16 time units. So if you want to figure out the waiting time, just subtract its burst time from that total time. So 16 minus 7, well, that's 9, so it must have been waiting for 9 time units. So process 2 waited for 1 time unit right here. Process 3 waited for 0, and then process 4 waited for 2 time units right here. So our average waiting time in this case is 3, which is, an improvement over what we had before without preemptions, which was 4. So any questions about that? Yep.
Is the time it takes to context switch like negligible compared to actually running the process? Like, I feel like we switch a lot of times, so it takes a long time to switch.
Yeah.
And we kind of get losing.
Yeah, so for this, I'm assuming context switching is instant. So in general, one of the things you want to report with your scheduling is how many times does it context switch. So we'll see that with our real algorithm. So this is, as far as I will get today, round robin. So far we haven't handled fairness, and it's a trade-off with the other metrics anyways. So we do something like round robin. So that's like if you have a toy sibling, you each get 30 minutes with it. You have it for 30 minutes, you pass it around, they get 30 minutes, and then if there's a third sibling, they get it, and then it goes back to the first person, just goes around in a circle. So that's what round robin is, but we have fancier terms for it. So the operating system divides execution into time slices. For some reason, they're computer scientists, so they want to use fancy terms, so they'll call them quanta, and the time slice will be called a quantum. Why? I don't know. They want to be fancy and sound smart. Really, it's just a time slice, a set amount of time. So with this, we maintain a FIFO queue of processes similar to first come, first serve, and we just give each process a time slice, and if it's not done yet, we preempt it at the end of its time slice and add it to the back of the queue. And then we just keep on going over and over again. So what are some practical considerations for determining the time slice or quantum length? So I heard one already a bit. If it's too low, you'll have a lot of context switches. And if the time it takes for context switch is like even comparable to the quantum length, you're just going to spend all your time context switching, and it's going to be real bad. So what is the opposite problem if my time slice is absolutely gigantic? Yeah. So what if the time slice was even longer than the process ran for?
It'll leave like empty CPU time unused, which kind of lowers the efficiency.
Yeah, so the time slice, you don't have to use all the time slice. So if you end early and terminate, well, the next process, the scheduler would just know that and then schedule something else to run, so it wouldn't be idle for the rest of the time slice. Yep.
What if the process is sleeping and it gets to its time slice? Would it just wait in the time slice, or would it just pass it?
So yeah, the question, how would sleeping play into this? So sleeping, it would just give up its time slice probably. Yeah.
You're not maximizing your throughput.
Not maximizing my throughput. Close. So at the beginning, we saw first come, first serve, right? And said it was really kind of crappy. So if my time slice is longer than what any one process executes for, what does round robin become? Yeah, it becomes first come, first serve, right? If my quantum length is like 8 years or something like that, then, well, guess what? It's first come, first serve because the process is just going to run until it's terminated, and the only thing to differentiate them is your arrival time. So there's a trade-off here. You don't want the time slice to be too low. You also don't want it to be too big. So this is as hard as it will get today, too. Well, we'll get it a little harder after this, but we're going to do the same scheduling, but we're just going to say, for instance, that the quantum length is 3 time units. So this might look like a bit of writing, so we will go over it. So here we go with the same schedule. I will have all the arrival times written on the top, and then a nice trick to do for round robin is to write the queue on the bottom. So you keep track of your queue at all the time, and then you know what to schedule next. So at time 0, P1 arrives. It would be the only thing in the queue, so it would get scheduled. And here our time slice is equal to 3. So P1 is the only thing to run, so we would run it for 3 time units unless it terminates early. But in this case, its burst time is 7, so it's going to still want to run after its 3 time units. So we would schedule it for 3 time units. And at time 2, our queue would be empty and P2 would arrive. So it would be the first thing in the queue. And then here, whenever P1 is done its time slice, it still wants to execute. So we would throw it to the back of the queue. So at time 3, our queue would be P2, then P1. So if we want to figure out what to run next, it's just whatever is at the front of the queue. So the next process to run is P2. So P2 would run for its 3 time units. And during that, well, at time 4, I would have P1 at the front of the queue, and then P3 arrives, so it would go at the end. So my queue would look like P1, P3, and then nothing. And then at time 5, P4 arrives, so it would go to the end of the line. So we would have P1, P3, then P4. So at time 6 here, I have to make its process 2 is done with its time slice, so I have to schedule another process. What one should I run?
P1.
P1, it is at the front of the queue, so I would run P1. Also, P2 is still executing, so I would put it, P2 is done, so I would put it at the back of the queue. So I execute P1 for 3 time units. It still wants to execute a bit more, but it has done its time slice, so it goes to the back. So my queue would be P3, P4, P2, and then P1. Now it's P3's turn. It only executes for 1 time unit, then it terminates. So the scheduler has to reschedule something, and the new process wouldn't just get the remaining time slice, it would get restarted. So P4 would go and get 4 time units here. And then our queue would look like P2, P1, then P4. So the reason why P4 gets a brand new time slice and not just continue and it kind of just uses the remaining 2 is, well, if you were malicious about it and you could figure out how big the time slice was, well, say the time slice was 10 units and another process just got whatever the remaining time was, well, I could time my process so that after 9 time units, it does something that causes a sleep, and then the scheduler makes a new decision and then gives that new process a single time unit, and then it reschedules me, and I get my full 10 again. Then I go, wait for 9, go to sleep, it gets 1, I get 9, 9, 1, 9, 1. So you could kind of game the system if the time slice just didn't restart every time. So In this case, P2 would run for its one remaining time unit, then P1, then P4. And now we're done. Yep.
Wait, so basically, the reason why P4 immediately gained a new time slice is that basically we somehow knew that P3 ended there and
Yeah, so you're the,
decided to make a new time slice.
yeah,
starting that.
so the scheduler is done by the kernel. So P3 would terminate, the kernel would know about it, and just start a new time slice.
Interesting, thank you.
All right. So now we have our fun math questions. So first would be average waiting time. So our average waiting time, well, we can do that trick again. So this is 16. So P4 ends here. P1 ends at 15. Oops. P2 ends at 14. And P3, it's somewhere there I can count. So process 1 was around for 15 time units. It executed for 7 of those, so it must have waited for 8. Process 2 was around for 14 here, minus 2 when it arrived, so it was around for 12. And it executed for 4 of those based off its burst time, so it must have been waiting for 8. Well, that is a really horrible 8. Then process 3, well, how long did it wait for? So it came in at time 4, and it waited for 1, 2, 3, 4, 5 time units. Then process 4, it ended at 16, arrived at 5, so it was around for 11 time units, executed for 4 of those. So if I can do math, 11 minus 4, hopefully it was waiting around for 7. So my average waiting time would be all this, which would be 7. So the next thing to calculate is the average response time. So average response is, again, the response time is the time that the process arrived to the time it first started executing. So for process 1, it arrived at time 0 and started executing immediately, so its response time was 0. For process 2, it arrived at here, where's the highlighter? It arrived at time 2, and it started executing at time 3, so its response time was 1. Process 3, again, waited around for the same 5 time units that are there highlighted in green. And then process 4 arrived at time 5 and didn't start executing until, let's just count. 1, 2, 3, 4, 5. So it also, its response time was also 5. So if we divide that by 4, we get 2.75, something like that. So the last thing that you calculate is the number of context switches. So to calculate the number of context switches, you just count the number of times in the schedule that we had to change between processes. So we don't count time 0, and we don't count time 16. So the quickest way to do this, or the most obvious way, is to just do a red line whenever we change between processes. So we change between process 1 and 2 there, then we change between 2 and 1, then 1 and 3, then 3 and 4, then 4 and 2, then 2 and 1, then 1 and 4. Then to count the number of context switches, we just count the number of red lines. So how many context switches do we have there? 7. So that would be what you would have to do on an exam. Yeah.
But theoretically, the numbers look horrible.
The numbers look horrible.
Yeah, like.
Why do they look horrible?
It's worse than like all those methods we introduced before, no?
So the other methods we introduced before, aside from first come, first serve, you couldn't implement them because you don't know how long a process is going to run for.
Oh, that's interesting.
So, yeah, so far this is the first one we can run. So, in order to make this the hardest thing we can do today, we'll do the same thing, round robin. Well, the time slice is 1. So this is as hard as it gets for today, and as hard as these scheduling questions get. So, starts off the same thing. Drawing the queue at the bottom is going to save us. So, process 1, it arrives at time 0. It's the only thing in the queue. So we would execute process 1. Whoops. Then its time slice is 1. It would go to the back of the queue. Guess what? It's still the only process. So we scheduled process 1. Now we have an instance of a tie. So you might think we could do process 2, process 1, or process 1, then process 2. So if there's a case where you're re-queuing an old process and a new process is arriving at the same time, you favor the newly arriving process. Why? Well, the other thing already ran, and if I favor the new process, I'm going to get an overall lower average response time. So generally, for these tie-breaking rules, there's generally a reason for them. So the why in this case is, well, I'll favor the new one because I want a lower average response time. So P2 arrives, so we would favor that newly arriving process and then put P1 behind it. So that would be our queue at time 2. So we would pick P2 to run immediately. So P2 would run. It would get thrown to the back of the queue. Then P1 would run. Then same thing is going to happen. So P3 arrives. So P3 doesn't get to butt ahead of P2 because it was already at the front of the queue whenever it arrived. So it doesn't get to butt ahead or anything like that. So after that, we would get P3 would go because it's the newly arriving process, and then our requeue of process 1. So then we would have scheduled process 2 to run. Same thing is going to happen. P4 arrives, so our queue would have been P3, P1, because they were already in the queue when P4 arrived. Now P2 is getting requeued, so it would be favored over the newly arriving P4. So our queue would now look like this. So after this, P3 would run. Mercifully, it only runs for 1 time unit, so it would be done, and our queue now gets shortened to P1, P4, P2. So after that, then P1 would run, P4 would run, and hopefully at this point I don't have to redraw the queue because it's just going to go around and around in the order 1, 4, 2, 1, 4, 2 until eventually they're done. So at this point with process 2, it has run for a total of 3 time units. So it's thankfully almost done. So we go another round of P1, P4, P2, and now P2 is mercifully done, and our queue would look like P1, P4. So now we just cycled between them, P4, P1, P4, P1, P4, and now they are mercifully all done. So this is as hard as it gets. Yep. Yeah, so right here, if we could take like fractional, so at like time 3.5, our queue would just be P2 on our queue, right? That would be the only thing in our queue. So if it's the only thing on our queue, when time 4 rolls around, well, we just put P3, the newly arriving one, after P2, and then the requeue of P1 at the very end. Yeah. Okay, so now we have to do the fun part. Average waiting time. Thankfully, I showed you a shortcut, which is much easier to do when you are writing it than if I am explaining it to you. So, at 16, P4 ended. 15, P1 ended. This is 14, 13. So at 12, P2 ended. So average waiting time. So P1 was around from 15 to 0. So it was around for 15 time units. Its burst time was 7. So it waited around for 8 time units. Process 2 ended at 12. It started at 2. So it was around for 10 time units minus the 4 it was executing for, so it must have been waiting around for 6 time units. Process 3, well, we can just look at it up there. It arrived at time 4, started executing at time 5, so it was only waiting around for 1 time unit. Then process 4, it ended at 16, came in at 5, so it was hanging around for 11 time units. 11 minus the 4 it must have been executing for means it must have been waiting around for 7. So divide that by 4 processes, our average waiting time is now 5.5. So, which compared to before, hey, it went down a little bit. So from 7, it went to 5.5. Next fun one is the average response. So in this case, P1 started executing immediately. Its response time was 0. P2 also started executing immediately. It came in at 2, started executing at 2. So its response was 0. Process 3, well, its waiting time was 1, so that was also its response time. It was just waiting around for 1 time unit. Last one is process 4, which process 4 we can see here was just, whoops, wrong color. It was just waiting around for 2 time units. It came in at 5, waited for 2 time units. So if we crunch the numbers here, our average response time is now 0.75, which is way better than before, which was 2.75. So last thing we have to get is the number of context switches, which is real fun. So, number of context switches. Same thing, we'll use our good old red line and start counting. So, 0 doesn't count, so, and also changing from process 1 to process 1, that is not a context switch. So, the scheduler would be like same process, not a context switch. So, whoops. So, this is our first context switch here. So, our first context switch, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 context switches. So that's as hard as it gets. So lots of context switches here, but we can see the trade-off of more context switches, but our response time was way better. Yep.
How long would a context switch usually be?
So remember we talked about context switching just being essentially a waste of time. So for real systems, context switches will be less than like 1% of the total time executing.
Which is basically negligible?
Yeah, which is fairly negligible, right? So if you're tweaking the time slice number and then you see that, hey, 50% of the time is spent doing context switches, well, you're not in the 1% range, so you should probably increase your time slice because you're switching way too fast. So there's always going to be some type of trade-off here. Oops. So any questions about that? Fairly straightforward, something we could do in an exam, get some free marks, feel good about ourselves. Much better than the forking examples where I can just like throw a billion forks at you. Yeah, so this is the easy part that shouldn't be too bad, and then you'll get a fork question, and then while you're thinking about it, you can do this question. So, could go through, do it again if you really want. Quantum length of 10 units. Guess what? That becomes first come, first serve. If you want to count the times again, I don't suggest it, but if you want to practice it, go ahead, and these are the numbers you should get for when it becomes essentially first come, first serve. So, like we said before, so the round robin performance depends on the quantum length and the length of the actual processes. So, generally is low response time, good interactivity, it's fair, low-ish average waiting time when the job lengths vary, but the performance depends on the quantum length. We have to set it. It's kind of difficult to set in practice. So too high becomes first come, first serve. Too low, too many context switches, which is just overhead. And in general, it also has, if you simulated a bunch, it has poor average waiting time if the jobs are all fairly similar length. So that's it. Scheduling just involves a bunch of trade-offs. We saw some different algorithms, if you could even call them that. First come, first serve, which is a valid scheduling algorithm if you just have to make a decision. Then we saw shortest job first, if we want to have no preemptions and minimize waiting time. Then we added preemptions, tweaked it a bit, got shortest remaining time first, then saw that minimized waiting time. Then we saw round robin, which is more fair. We can implement it. Yep.
Could you reiterate on the concept of overhead? I don't think I.
So the cause of overhead is just the amount of time wasted not doing useful work. So if you were the kernel, your useful work is running applications.
But you said it's pretty short, no? Like the context switch.
The context switch on your system is pretty short, but if you get to pick the length, you can pick wrong.
Sorry?
If you get to pick the quantum length, you could pick wrong, right?
Pick wrong?
So you could pick a quantum length that's too short, where the context switch time matters.
Oh, interesting. Thank you.
So you don't want to do that. So yeah, any other questions? We can end early, take a sigh of relief. Some of you have been working on lab 2, so you can do that. Yeah.
So are the shortest job and shortest remaining time used today? Because
Yeah,
they both are, they have the potential for starvation.
Yeah, so shortest remaining time first, not going to be used because we don't know the burst time of processes for one. And then another reason is that starvation's an issue, so we wouldn't use it. And you wouldn't actually know the times ahead of time. So it's like kind of an after the fact theoretical thing. Yeah. So it just restarts a new time slice because if you knew the quantum length, you could essentially game the system where, say it was like 10 time units, you can just wait till you're almost done your quantum length, give up the CPU, then some other process just gets it for like 1 time unit, something really short, and then if it's just you and another process, you get it back. And you get a full new time slice, and then you use it, almost all of it, let them get the remainder, then you use all of it. I punched the microphone again, god damn it. All right. Yeah, so in general, for round robin, you just always restart the time slice. You just always restart the time slice, yeah. Yeah, you don't want anyone gaming the system or doing anything weird. So, with that,
And this is still assuming that each process takes up the whole CPU.
yeah, so this is assuming a single CPU core. So, we'll get into more advanced stuff tomorrow, but for scheduling, everything's just a big trade-off. So there's no right answer for scheduling. So just remember, pulling for you.